Hello, you guys are the new physics students? Down the corridor, first classroom on the left. Good luck. What's your group here for? English? It says in the class you're looking for. Move along. What are you students here for? History? I've heard about you guys. You believe that if you study past cultures and past events, you can stop future things going wrong. I believe this semester you're studying the first Death Star. Your classroom is up there on the second Death Star. Take the shuttle, second bay, and good luck. You want to interview the Emperor? Okay, you might be in for a shock. Last group, more physics guys? Good. Down the corridor, first on the left. Have a good year and good luck. Okay, sorry about that, stormtrooper. I hope it didn't bother you too much. So we've already been studying projectiles and getting the basic ideas right in terms of using horizontal and vertical sort of separate motions. What we want to look at now is some of the finer points at stage 2. So first of all, when would you get the maximum range? I guess is the key thing here. And if you're only going from the same height to the same height, or uni-level projection, it's basically 45 degrees we're going to go for here. Because that will give you the best combination of range, because the range, horizontally, is the horizontal velocity times by the time. And it turns out that that product is at its best at 45 degrees, because you get the best combination of horizontal velocity and time. That's a combination there. Now you can actually show that because the horizontal velocity there is based on v cos theta, from your horizontal velocity formula, VH equals v cos theta. And the time in the air there would be a rearrangement of v equals v naught plus at. Okay? Where it actually stops at the top there, you've got your initial velocity. Now the initial velocity vertically there is v sine theta plus minus 9.8 times by t. So if you're rearranging for t, you'll find you get minus v sine theta over minus 9.8 is equal to t. The minus cancel that, but you can see it depends on v sine theta there. So you've got a v sine theta there over 9.8. Now it turns out the product of sine theta and cos theta is at its best for an angle of 45 degrees. That's when you'll get your best sort of size range there, and that's why you want to use 45 degrees if it's a uni-level projection. So just bear that in mind. For uni-level projections, you get the best product there at 45 degrees. Now it turns out if you actually go to a steeper angle there, say you were to try 60 degrees, people would say, well it's going to be more time in the air there because it's got a bigger vertical velocity. If it's got more time in the air, why doesn't it go further as an overall range? And the reason for that is that even though this property is going up, you'll find out that the horizontal velocity has actually, the size of that horizontal velocity has gone down by a lot. In fact, it goes down by a further amount than the time goes up. And as a product here, the overall product is less. And so it's not good to go to bigger angles bigger than 45. The converse is true. If you go to angles that are actually smaller than 45 and go to ones like 30 here and try 30 out, you will now get a bigger horizontal velocity component there because it's actually got more going in that direction. But you'll find the time there goes down by even more, and again you'll get a smaller range there going down overall. And so that was good. So that's something to bear in mind. Maximum range is at 45 degrees. Now let's take this one step further. It turns out you can get complementary angles giving you similar ranges or the same range. Because if you look at the last example here, if you do shoot something at 60 degrees there, like this, it'll go quite high, back down, and you'll get a range something like that, and so there's your range there. If you try something in the 30 degree mark there, then the complementary angle, because 60 plus 30 gives you 90, so they're complementary angles. If you were to try a 30 degree angle here and split the difference like that, people will go, it won't go the same range, but it does. Because what happens here is it's got a smaller time in the air, it doesn't go as high, but it does actually have a bigger horizontal velocity component. You'll find that they'll travel the same distance. That range of VH times T will give you exactly the same answer. One has a bigger horizontal velocity component, but the time goes down by the same amount. and you get equal values there for the two angles. So 60 and 30 will give you the same angle, even though they're not the same height and the same time. Things like 70, the complement to that will be 90 take 70 is actually 20. If you try 80, you'll get 10 degrees with the complement, which means it goes really, really high, and so it's in the air for a long time, but it hasn't got a very good horizontal component. Anyway, the product is the important thing to bear in mind when you're explaining these things. So other complementary angles, you could try 50 and 40, and so on. They're complements to each other. So that's the second point to bear in mind there. So you've got maximum range at 45, complementary angles at 70, 20, 60, 30, and so on, because of that product still being the same. Okay, last thing here. What happens if you decide to take the same situation that might be from ground height like that and actually elevate it? So let's say we had it going at, say, 20 metres a second at 60 degrees. What would happen if instead of doing this at ground level, we did it on elevated T? So you're actually launching it from a height above the ground like that. So would the range be the same from there to there? The answer to that is no, because what's going to happen here is that the object is going to continue to fall down past the original height, and it's got this extra time in the air. And while it's got the extra time in the air, it's going to actually travel further, because don't forget the range is horizontal velocity times by the time. And this is going to stay the same all the way through the trip, and what we've done here is made this time go larger, and therefore the displacement's going to go larger. So that's the sort of way you would argue it. You're going to get a larger displacement here now because it's longer in the air, and the range is the product of horizontal velocity and time, bigger range. So that's a simple way of doing it. So if you look at notes on this that I'll give you out, main things to bear in mind here is that the maximum range occurs when the launch angle is 45 degrees. At larger angles, the time of flight will increase, but the horizontal velocity component drops by an even larger amount, and at smaller angles, the opposite occurs. So your 45 degrees is your best product. Complementary angles will give you the same results, okay? 30 and 60 is the same range as each other, and 10 and 80. And if you go to a higher launch height, you're going to get longer in the air, and because range is horizontal velocity times by time, you're going to get a larger range because it's longer in the air. Okay, thanks.